In this lecture, we'll be discussing APA format, specifically how to format your statistical output so it can be published and universally interpreted by other experts within the field. Now, this presentation is 39 slides in length, so I'd recommend either skipping through it to the particular method output which interests you, or watching this lecture at double the speed. Also, I put a link in the description to my website from which these slides were created. The website entry, which was published on August 4th, 2019, that is the entry which contains the text contents of the slides. You can save yourself some time by going directly to the link. There's other articles in addition to APA format that might interest you. However, in the event that you're unable to do such, you can stick around and watch the presentation. And please remember to like and subscribe. In this video, we're going to specifically discuss the t-test, ANOVA, Pearson correlation, chi-square, and multiple regression analysis, and how to report the output of those methods in the APA format. So first, a bit about the APA format. APA format is the official style of the American Psychological Association, also known as APA, and is commonly used to cite sources in psychology, education, and social sciences. The APA style originated in a 1929 article published in Psychological Bulletin that laid out the basic guidelines. These guidelines were eventually expanded to the APA publication manual. So t-test, when to use it? There's a few variations of the t-test. There's the one-sample t-test, the two-sample t-test, the Welch's two-sample t-test, and the paired t-test. The one-sample t-test is utilized to compare a sample mean to a specific value. It is then used when the dependent variable is measured at the interval or ratio level. The two-sample t-test, this test functions in the same manner as the above test. However, in the case of this model, data is randomly sampled from different sets of items from two separate control groups. The Welch two-sample t-test, this test functions in the same manner as the above test, the only difference being this method is utilized if data is randomly sampled from different sets of items from two separate control groups of uneven size. The paired t-test is similar in composition to the two-sample t-test, and this test is utilized if you are sampling the same set twice, once for each variable. So in this instance, we're again utilizing the cakes example. A factory employee believes that the cakes produced within his factory are being manufactured with excess amounts of corn syrup, thus altering the taste. 10 cakes were sampled from the most recent batch and tested for corn syrup composition. Typically, each cake should comprise of 20% corn syrup. Utilizing 95% confidence interval, can we assume that the new batch of cakes contains more than a 20% composition of corn syrup? The levels of the sample were as follows. So if we input this data into R or R Commander, and we perform the appropriate analysis, this is the output from the RStudio output, you should receive something which resembles what's on the screen in the console window. So we have the mean, we have the standard deviation, we have the t-value, the degrees of freedom, and the p-value. So if we're going to report our data in the appropriate APA format so it could be universally interpreted, it would look something like this. First, we would state the test and the conditions of the test. So in this case, a one-sample t-test was conducted to compare the level of corn syrup in the current sample batch of cakes to the measured historical level of corn syrup contained within the previously manufactured cakes. And then our results would be, there was a significant increase in the amount of corn syrup in the recent batch of cakes. There we have the mean and the standard deviation at 2 decimal points, as compared to the historically assumed mean. There we have the mean value, the t-value. This is the degrees of freedom here. This is the t-value at 2 decimal points, and the p-value. In this case, our p is less than 0.01. So if you end up with a p-value which is less than 0.01, you just state it as such at 2 decimal places. And here's a breakdown of the structuring of the APA format without the results put in from our example test. There was a significant decrease in group A, M mean of group A, standard deviation equals standard deviation of group A as compared to the historically assumed mean, M equals historic mean, T degrees of freedom equals T value, P equals P value. Or there was not a significant increase with all the same values. So the main differentiation here is whether or not we rejected the null hypothesis or not. If the null hypothesis was rejected, our results would be formatted as such. And if our null hypothesis was not rejected, our results would be formatted in this second example here. Here is a two-sample t-test example. And we're going to go over the t-test methodology, application, etc. in later lectures. This is just for APA format. But again, I'll show you how to do all of this, how to structure the data, etc. This is just how to interpret the results. We'll be interpreting the results in those future lectures, but we'll be putting them in APA format, and I'll be operating under the assumption that you understand APA format, what it is, and how to utilize it. Okay? So in this example, it's a two-sample t-test. A scientist creates a chemical which he believes changes the temperature of water. He applies this chemical to water and takes the following measurements. He then applies the chemical, he then measures temperatures in the sample in which the chemical was not applied. So here it's being applied. Here is different samples where it's not applied. So applied, not applied, and the samples of each. Can the scientist conclude with 95% confidence that his chemical is in some way altering the temperature of the water? Here is our output. Again, we're interested in the T value, the degrees of freedom, the P value, the mean of the first sample, the standard deviation of the first sample, the mean of the second sample, and the standard deviation of the second sample. So here is the outcome of our method application. First, we're going to state the test which we had applied, the method, etc. A two-sample t-test was conducted to compare the temperature of water prior to the application of the chemical to the temperature of water subsequent to the application of the chemical. We see that there was a significant difference in the temperature of water prior to the application of the chemical. Here is the mean and the standard deviation. Okay, this is no chemical. Mean, standard deviation, as compared to the temperature of the water subsequent to the application of the chemical. So this is with the chemical. There's the mean, there's the standard deviation. It's the mean and standard deviation of each group of observations. All right? 14 is our degrees of freedom. This is our T value, T 2.46, and this is our P value, which in this case is less than 0.05, or remember, 2 decimal points, less than 0.05, but still greater than 0.01, so we just report it as is. But since it is less than our alpha value, we reject the null hypothesis, and that is why there was a significant difference, because the null hypothesis was rejected because the P value is less than the alpha value. More on that later. So this is how it's structured. If there's a significant difference for a two-taled, two-sample t-test, there was a significant difference in the group A, mean standard deviation, as compared to group B, mean standard deviation, T, degrees of freedom, T value, P value. And the difference between this example or this output and this output, as far as APA format is concerned, is for this, the null hypothesis was rejected, so there was a significant difference. And for this, we failed to reject the null hypothesis. Remember, we either reject the null hypothesis or we fail to reject the null hypothesis. We don't accept the null hypothesis. It's either rejected or failed to reject. Here is a paired t-test example. A watch manufacturer believes that by changing to a new battery supplier, that the watches that are shipped, which initially which included an initial battery, will maintain longer lifespan. To test this theory, 12 watches are tested for the duration of the lifespan with the original battery. The same 12 watches are then retested for the duration with the new battery. So we have watches which are being tested. This is with N1 is the condition of the old battery, and N2 is the new battery. Now with a paired t-test, it's the same watch twice. It's the same instance, but with a different application. So this is watch 1, watch 2, watch 3, watch 4, watch 5. And this is watch 1, old battery, new battery. Watch 2, old battery, new battery, and so on and so forth. So we have two observational groups. We apply the paired t-test. Here's our t-value, degrees of freedom, our p-value, which you can see is less than 0.05 if the alpha value is 0.05. Mean of the first series of observations, standard deviation of the first series of observations, mean of the second series of observations, standard deviation of the second series of observations. So here is our APA results. A paired t-test was conducted to test the lifespan duration of watches which contained the new battery to the lifespan of watches which contained the initial battery. There was a significant increase because we are rejecting the null hypothesis because 0.02 is less than 0.05. More on that in later lectures. There was a significant increase in the lifespan duration of watches which contain the new battery. So here's the new battery mean, the new battery standard deviation, as compared to the lifespan of the watches which contained the initial battery. Initial battery mean, initial battery standard deviation, degrees of freedom, t-value, p-value. Two significant figures in each instance, okay? And here is just the boilerplate without any information reported within it, okay? This is whether the null was rejected or the null was found to be rejected, okay? Right, looks like this one is about out of sorts. We'll go back to this later. This is correlation. Has nothing to do with the t-test. Looks like when I was putting my slides together, it ended up missorted. We will go back to this. But what we can talk about now is ANOVA. So what is an ANOVA? When do we use it? An ANOVA is a one-way analysis of variance, also known as ANOVA. An ANOVA model is going to contain a single independent variable. And we'll talk more about ANOVA in length in a later lecture, which will be dedicated just to the ANOVA process. But ANOVA, you can think of it sort of like a t-test, except with multiple categories, at least as far as the one-way ANOVA is concerned. So let's just do a quick example, and I'll show you how to put your results in the appropriate APA format. A chef wants to test if patrons prefer a soup which he prepares based on salt content. He prepares a limited experiment in which he creates three types of soup: soup with a low amount of salt, soup with a high amount of salt, and soup with a medium amount of salt. He then serves this soup to his customers and asks them to rate their satisfaction on a scale from 1 to 8. So for low soup, customers rated it 4, 1, and 8. So one customer rated it a 4, another customer rated it a 1, another customer rated it an 8. So these are separate instances of the low salt soup. So it was given to one customer, given to a second customer, given to a third customer. Medium salt soup, given to one customer, given to a second customer, third customer, fourth customer. High salt soup, you get the idea. Here's our console output. Now, this is a bit tricky because it's an ANOVA, and ANOVAs can be tricky, especially as we start getting into two-way ANOVAs or repeated measure ANOVAs. But in any instance, we have the degrees of freedom here, the residual degrees of freedom, the F value, and then this being our P value, all right? So if we're going to report our findings in a one-way ANOVA, we would state that there was a significant effect of the level of salt content on patron satisfaction at the P less than 0.05 level. And this would be whatever your alpha value is. All right. And these are your conditions. F2 of 2 and 7, that's the degrees of freedom here and the degrees of freedom here. This is your output in R. Here is the F value. We're rounding it to two significant figures. And here is your P value, which was taken from here, again, rounded. And this is how it would be resembled, whether or what the output would resemble, whether or not it was significant or not significant, whether we rejected the null hypothesis or failed to reject the null hypothesis. Two-way ANOVA, again, we'll cover it in a later lecture dedicated just to the method. But in any event, a two-way ANOVA is a two-way analysis of variance. It's an ANOVA model containing multiple independent variables. What that means will be clear after we go through this particular example. Researchers want to test study habits within two schools as they pertain to student life satisfaction. The researchers also believe that the school that each group of students is attending may also have an impact on study habits. Students from each school are assigned study material, which in sum totals to 1 hour, 2 hours, 3 hours on a daily basis. Measured is the satisfaction of each student group on a scale from 1 to 10 after a 1-month duration. And we're going to be assuming 95% confidence interval. So here are students from school A who studied for 1 hour, 7, 2, 10, 2, 2. Here are students from school B who studied for 1 hour, 8, 5, 1, 3, 10. We have multiple hypotheses for a two-way ANOVA. So as a result of such, we have a whole lot going on in our output as it pertains to each particular hypothesis, which is being tested. This is for study time. This is for school. This is for the interaction effect. This is residuals. Here is the F value and the P value for each. Now, we were going to report this. We would say there was a significant effect as it pertains to study time impacting student stress at the P less than 0.05 levels is your alpha value. For the three conditions, F values, degrees of freedom, F value, P value. There was not a significant effect as it relates to school attended impacting student stress levels at the P less than 0.05 level for the two conditions. And finally, there was not a statistically significant interaction effect on the school variable, on the study time variable at the P less than 0.05 level. And these are the hypotheses here. This is study time, which as you can see is less than 0.05. This is school, which as you can see here is greater than 0.05. And this is the interaction hypothesis, which we'll talk about again in far greater detail later on, greater than 0.05. Here are the F values for each of those hypotheses. And here are our degrees of freedom, 2, 1, 2, and there's the 24. So 2, 24, 1, 24, 2, 24. And if you need help or if this is going a bit quickly, just pause and take a look. And here is each hypothesis listed out. It's whether or not there was a significant effect or not. And that all has to do with whether the hypothesis is rejected, null hypothesis is rejected, or failed to be rejected. So here's rejected, 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 and here's failed to be rejected, failed to be rejected, failed to be rejected. And here is the category, the first category, the second category, and the interaction. First category, second category, interaction. So our first category was study time, second category was school attended, and then the interaction of the two. Study time, school, interaction of the two. And just formatted it appropriately. Pearson, which again will have its own bit of lectures when we get there in this playlist. Make sure you check out the playlist if you haven't been checking it out already. But the Pearson coefficient of correlation is a method which tests variables for correlation. So was there a certain correlation between the two variables, X and Y? Here is our output. As you can see, there's a whole lot going on. Here is our t-value, our degrees of freedom, our p-value. Here is our means for each. Here's our mean for X. Here's our standard deviation for X. Here's our mean for Y. Here's our standard deviation for Y. And here's how we would state a correlation outcome. So there was a positive correlation between the two variables. X, you have the number of observations, which was 10. Y, the number of observations is 10. Here's X, here's the mean and standard deviation, similar to that of the t-test. Y, mean and standard deviation. Conditions, here's our degrees of freedom. All right, here is our t-value right there. Here's our p-value, which is less than 0.05. All right, and then we have to, excuse me, we have to state the Pearson product moment correlation coefficient. That is demonstrating the strength of the correlation. So there might be a correlation, but then we have to see or assess how strong the correlation is. And that's determined by the Pearson product moment correlation R value, which is 0.65, and that is right here. Two significant figures, okay? And finally, well, actually, we have one more after this, which is the multiple regression analysis, but not last, and certainly important, is the chi-square. CHI is chi. Don't say chi, please. Don't ever say chi. We're somewhere in the internet ether. I'll cry a single solitary tear. All right. Chi-square is a test which measures categorical significance as it pertains to a binary outcome variable. Important stuff. We'll talk about it in later lectures. Here's an example. While working as a statistician at a local university, you are tasked to evaluate, based on survey data, the level of job satisfaction that each member of staff currently has for their occupational role. And we're assuming a 95% confidence interval, which means if you watched the prior lectures, that is an alpha value of 0.05 because it's 1 minus 0.95. The data which you gather from the survey is as follows. General faculty, we have the number of satisfied and unsatisfied. Professors, number of satisfied and unsatisfied. Adjunct, satisfied and unsatisfied. Custodian, satisfied and unsatisfied. And in this case, we have 150 members of general faculty, 50 professors, 100 adjuncts, and 30 custodians. Here is our output for the Pearson chi-squared test. We have our x squared value, the degrees of freedom, and the p-value, which in this case you can see definitely is lower than not only 0.05, but lower than 0.01. So this is how we report our results. Again, two significant figures. A chi-square test of independence was performed to examine the relation between occupational role and job satisfaction. The relation between these variables was found to be significant at the p less than 0.05 level. Remember, our alpha value is 0.05. X squared, or chi-squared, all right, so get the chi symbol going. It's going to be a, you're going to have to cover a couple of keys on your keyboard to get that, or look up chi and then copy and paste it from Google. At the chi-square, 3 is the degrees of freedom. N is the number of observations across all observational categories. So it's the sum of these, and these all added together, each group. each category together, okay? 150 plus 50 plus 100 plus 30 is 330. The x squared, or the chi-square value is here. All right, we're rounding it up. And the p-value is less than 0.01. So if it's less than 0.01, we don't give the figure. We just say it's less than 0.01, and there we are. And it is found to be significant because it's less than our alpha value, which was 0.05. And here is what the chi-square format resembles when it's in its most generic, without us having populated anything within it. And this is going to be your alpha value here. So it's not always going to be less than 0.05 if you have an alpha value of 0.10. Obviously, that will be the value that you put here. But everything else, you're going to just fill in with whatever your data is from the output of your test. And whether or not it's significant or not significant depends on whether or not the null hypothesis was rejected or we failed to reject it. Now, finally, we come to multiple regression analysis. When do we use it? We use it when continuous outcome variables. We use it to build models for those variables, and we use it to look for relationships between the variables and the models of the variables together. So we'll, again, get into this in a later lecture, which will be dedicated just to this topic. But for the sake of this lecture, I'm assuming you have some understanding of the linear regression. And we've already got it applied, and we've already got output. And what we're looking at particularly here is this intercept value. X is value here for the coefficient, Z, because we have Y, X, and Z. Y is our dependent variable, X and Z are our independent variables. All right. And we're looking at the significance primarily for X and Z. Now down here, we're interested in the multiple R square value. And we'll talk about what variable significance, how that functions in the grand scheme of things with these models in a later lecture. But in any event, let's report our findings. So a linear regression model was utilized to test if variables X and Z significantly predicted outcomes within the observation of Y, included within the sample data set. Now, if you're working not just with variables, but actual, actual situations, these variables here would be whatever those aspects of the formula which you're looking to report, you would place them there. So for example, if we're looking to significantly predict the outcomes of home runs, and we're trying to test if, say, batter height and batter weight impact that, that's what you would place here instead of X, Y, and Z. You'd say a linear regression model was used to test if variables player height and player weight significantly predicted the outcomes within the observation of home runs included within the sample data set. The results indicated that while X, okay, and here is the one value and the significance, is a significant predictor variable, the overall model itself does not possess a worthwhile predictive capacity. Predictive capacity is going to be the R squared value. So as you can see, our R squared value is low here. This is not the same as P value. We'll go into it later. But you have to determine as to whether or not the model possesses a worthwhile predictive capacity. R squared value will be here. That is determined by that. And then you have to report as to whether or not, within the context of the model, whether the variables within the model are looked at as being significant. Okay? And this is the general format for such. So we'll talk all about this in later lectures. We'll go into examples. We'll go into what exactly each method, when it's appropriate, how to apply it, how to interpret your results. We'll use RStudio and we'll use RCommander. to apply the methodology. And if you made it this far, again, please consider liking and subscribing. And if you wanted just the contents of the slides, please visit the website within the video description link below. All right, so that is it. Hope this was able to help you out. I hope you have a wonderful day. Take care.